Hi everyone, and welcome to a new edition of Digital Days. Today, we will be focusing on common mode chokes, how to characterize them, and a selection guide for different applications. My colleague Ivan Arias and I, Asir Chen, will be guiding you through this presentation. So the agenda is as follows. We'll start by providing some context on common mode chokes, then we will move on to how they can be characterized, followed by the selection process for different applications. We'd like to end the presentation with a showcase of a practical example based on our broad portfolio. So first of all, what's a common mode choke? A common mode choke is a passive component that consists of two windings on a shared magnetic core. The purpose is to attenuate the common mode current while allowing the differential mode current to pass unaffected. The differential mode current is our useful signal. In other words, it effectively suppresses noise without distorting our desired signal. Here in the drawing, you can see the main parts of a common mode choke. At least we have two windings, then we've got a ferrite core, and a case with pads for PCB soldering or pins. So in a common mode choke, we have two different winding styles, and each of them is relevant to its intended application. On the left side, you can see that we have a bifilar winding where the wires are wound together. This provides the lowest attenuation in differential mode, which is especially critical for data lanes and high-speed signals. On the right side, you can see the sectional winding where the windings are separated. While this has stronger effect on the differential signal, it offers improved isolation, making it particularly useful for DC lines and low-power applications. Here in the picture, we show you an example from a simulation that illustrates the leakage inductance of each winding style. As you can see, it's much higher in the sectional winding. This is due to the separation of the windings.
To understand the common mode choke characterization and selection, we must start asking ourselves, why a common mode choke? And the main reason to use a common mode choke is to suppress the common mode noise generated by the circuit or noise received by the PCB tracks, maintaining the signal and power integrity, ensuring compliance of the electronic design with the standards during the testing phase. When it comes to reduce noise in low power or data lines, there are several alternatives. But common mode chokes integrates real inductance into each line, acting both in differential and common mode. This makes them ideal when reliable and repeatable filtering is required in electronic designs. This comparison here is explained in detail in the Blue Electronics application note ANP 146. We have summarized the benefit of using common mode chokes by some of the most popular applications and in which frequency the noise could be located. This table is valuable when we don't have the tools or the possibility to measure and analyze the noise spectrum directly. Instead, it gave us a starting point to choose a right common mode choke. For example, in power supplies, one of the main noise sources comes from the active switching of transistors. This generates sharp edges in high-frequency disturbances that easily couple into both the input and output line. A common mode choke is highly beneficial here because it provides external attenuation in these unwanted signals while maintaining the integrity of the DC power path. So, this table is not the final answer, but a very useful guide to make the first filtering decision with confidence. We have several series in our portfolio, and in the first interaction could be very overwhelming. How can I choose the right common mode choke for my design? That is why it is organized into different series. Some series are specifically designed for DC lines, others for data lines, and some can be used for both. This flexibility comes from one of the common mode choke's characteristics, and is the winding style, which can be bifilar or sectional. As explained earlier, the winding style impacts the differential mode signal while also influencing key parameters such as the insulation level. To access our common mode choke portfolio, just visit our website under EMC component, then navigate to CMC for data line and low voltage. There you will find all the series clearly indicating whether they are bifilar or sectional, along with their electrical parameters. For a more detailed overview and easy benchmark, you can use our platform RedExpert. We will show you how the tool works later in a practical example.
So let's talk now about the characterization of the camel mode chokes. For the camel mode choke design, we focus on a few key parameters. As you can see here, the wire thickness and isolation, also the number of turns. We also have the core material, then the pads of the pins for the PCB soldering, and the case. Through the definition of these parameters, we provide a clear framework for both the electrical specifications we are targeting and the physical dimensions of the component. Through a combination of simulations and production processes, we are able to achieve the target values of each one of these parameters. And finally, we will define the final design. In this slide, we focus on inductance and leakage inductance in camel mode chokes. The core material in geometry are the main factors defining the camel mode inductance, while the winding style, either bifilar or sectional as it was explained, controls the coupling factor. In general, a higher coupling means a lower leakage inductance. When it comes to the limitations, there are a few important aspects to highlight. The measurement frequency of the LCR must always be noted, typically 10 kHz or 100 kHz. The inductance values vary significantly with the frequency, so it's important not to extrapolate blindly. For leakage inductance, measurements must be taken with the windings connected in differential mode, not in camel mode. Finally, it's important to note that the tolerance for inductance is usually quite high, typically in the range of 25 to 50%. Now, let's take a look at impedance versus frequency. The frequency response is mainly determined by the core losses and the permeability of the material. Additionally, the interwinding capacitance, which depends on factors like spacing or layer buildup, defines the resonances and the high-frequency roll-off. Regarding limitations, we need to keep in mind that the fixture is needed to perform both differential mode and camel mode measurements, and a proper calibration process is essential to ensure reliable results. Finally, note that the curves presented here are typical values and may vary depending on the specific component and conditions. Now let's talk about the rated current. The rated current of a choke is influenced by several physical factors. The wire cross-section, which determines the conduction losses. The core cross-section material, which impact both saturation and core losses. And the PCB footprint and copper planes, which define the heat dissipation capacity. As for limitations, it's important to remember that the rated current is not a universal constant. It strongly depends on the PCB design, the cooling conditions, and the ambient temperature. Finally, we'd like to note that the thermal rise limit is specified in the datasheet as a delta of 40 K. Let's now look at the DCR or DC resistance. From a physical standpoint, the wire diameter and length, which relates to the number of turns, are directly proportional to the copper resistance. In addition, the pad design and solder terminations can introduce extra milliohm contributions. There are also some limitations to keep in mind. The DCR has a clear temperature dependency. For example, copper increases by about 0.39% per degree. Contact resistance during measurement can distort results, especially at low values. Finally, note that a fixture is required for this measurement, and the maximum DCR value is specified in the datasheet, representing the worst-case scenario for losses. And finally, let's review the S parameters, in this case S11 and S21, also called return losses and insertion losses. Physically, all the choke elements, the core, the wire, the interwinding capacitance, and even the pads, can be represented as a 4-port network. This approach helps us understand both the insertion loss and the return loss when the choke is integrated into a real circuit. There are, however, some limitations. Measuring S parameters requires a proper 4-port setup with full calibration to ensure accuracy. And it's important to remember that S parameters are linear frequency domain measurements. They don't capture saturation effects or thermal behavior. These explained parameters are relevant depending on the applications. For example, for these data applications, we will want to look for a common mode choke for data lines. In this case, minimal leakage inductance and low interwinding capacitance. This ensures that the signal of interest, in our case the differential mode, remains unaffected, while effectively filtering common mode noise generated by high-speed interface. Here, as you can see, a USB example and an Ethernet example designs. For DC filter applications, the rated current parameter is one of the focus, now that the current will be applied constantly on the windings. The recommended PCB design is to place the common mode choke as close as possible to the connector. This way, we will block the noise at the entry and exit point of the system, preventing it from propagating through the PCB or radiating to the outside. In the example of an LED lighting matrix, we see extra protection diodes and capacitors together with a choke, and we combine three functions here. The diode protects against reverse polarity or surges, capacitors provide local shunting of high-frequency noise, and the choke stops the common mode disturbances from leaving or entering through the cable. This ensures both EMI compliance and long-term reliability of the LED system. In a mixed application, we implemented our SL5 series, selected for its high rated current value and its ability to provide both common mode and differential mode attenuation at the desired frequencies.
For a general case, when selecting a common mode choke, several factors must be considered. The designer should have the application constraints clear and must start from the main one. That could depend on the design phase. For example, if the PCB has been already defined, the available space will be a critical constraint. If we are still defining the PCB, we could start for the working current that will define the rated current, or with the working voltage that will define the rated voltage. Next, it is essential to clearly define the application, whether the common mode choke is for data, DC, or both. The winding style plays a key role in selecting the right common mode choke for the applications, as we have explained before. For the next step, we must remember that the signal is transmitted in differential mode and the noise we aim to suppress is in common mode. It is important to choose a common mode choke that has the highest common mode impedance at the noise and its harmonics frequency. And if it is for data, that has the lowest differential mode impedance as at the transmission frequency. For DC application, a high impedance in both modes could help reject all the noise. Finally, you need to verify that the DC resistance included in the common mode choke will not affect your signal or voltage level, and ensure that the EMC performance meets the required standard.
Now we would like to show you a practical example. In this case, I will be the customer and Ivan will be the engineer that shows me how to choose the proper common mode choke. So Ivan, I'm developing an industrial machine control that uses an LED screen. However, I'm facing an issue. There's electromagnetic noise affecting the screen and causing flicker. These are my specifications and my limitations in terms of space. And this is the graph I'm getting where you can see the noise peaks. Okay, would you like to help me choosing a common mode choke?
Sure, no problem. So the first thing that we need is what you already shared with me, the specifications of your design, and also where you have your problem, where is the noise located. So with this information, we go directly to our tool, to Red Expert, and we start filtering using this specification. So first, you told me that you need that this common mode choke, withstands 24 volts. So this will be a minimum. So we need that this will be from 24 up. We have our first filter, and we already pre-selected some of the chokes that we have in the catalog. The second will be the rated current. Here we also have a minimum. It will be 2.5 or more. So here we have another selection. And the last one that you have is the space constraint that you have. So for this, this would not be a minimum, but a maximum. This will be the maximum dimensions that the common mode choke that will help you have or will have. So we put here maximum 10 millimeters, maximum 10 millimeters, and in height, maximum 4.5. So if you see with these specifications, we already have pre-selected several of our part numbers. So what we need to do now is to check the performance of these common mode chokes in frequency. Here we have, it will be maximum 4, so we will keep it up until 3.5. So now if we take a look into the graphic that you are showing me, you need to have the mouse impedance from 150 megas up to 1 gigahertz. So with this information, we go to the graphic where we are showing the impedance that the common mode choke is putting to the noise in frequency. So we have our two best options here is the 132 and the 102.
Okay.
Now what we need to check if these common mode chokes are not going to affect your signal by applying some physical resistance to the circuit. So we need to go and calculate to the datasheet to check the DC resistance and to calculate the voltage drop. So here we have calculated both of the voltage drop using the DC resistance, and my opinion here is that you should use the one that is putting less voltage drop into your line. So what you need to do now is to take this common mode choke, put it in your PCB, and check again the response in frequency. How is this filtering the noise? So just go check that and come back to me if you have any questions.
Okay, thank you very much, Ivan. I will test it in the laboratory and share with you again the results. Okay, so this will be my graph after the new test. And yeah, as you can see, it worked. So it was a proper common mode choke. I could filter my noise, so we cannot see the peaks anymore. So thank you very much, Ivan. Thank you for the help.
Not a problem. Here is the most important thing is that it's filtering, you are passing the standard, and also your signal is not being affected. So if this is working, perfect. You can go and buy the common mode choke selected.
Before finishing this presentation, we'd like to show you our newest releases. As you know, we are constantly expanding our portfolio with new solutions. Here, you can see our latest releases. First of all, we have expanded our CMSW series with a new size, the 1210, which is specially developed for special data line applications such as CAN. Then we have expanded our CMDC series, which is designed for higher DC current applications while keeping the package as compact as possible. For more details, we invite you to visit our website. Thank you for your time, and now we will be happy to answer your questions.